Welcome, everyone, to today's session. We are here to explore a blueprint for secure Azure authentication in Go. Our focus will be on mastering the Azure Identity SDK, guiding you through the entire process from understanding the initial architectural landscape to implementing robust solutions in a production environment. Let's dive into how you can build secure and reliable connections between your Go applications and the Azure ecosystem. In Part 1, we will explore the authentication landscape by understanding the full spectrum of credentials available within the Azure Identity SDK for Go. This section provides a comprehensive overview of the various authentication mechanisms at your disposal, ensuring you can select the most appropriate credential type for your specific development and deployment environments. The Azure Identity SDK offers a versatile range of credential types designed to simplify authentication across various environments and scenarios. Starting with environment-based authentication, the Environment Credential class allows applications to authenticate using configurations stored in environment variables, providing a flexible way to manage settings without hardcoding. For service-to-service communication, we have service principal credentials. This category includes client secret credential, client certificate credential, and client assertion credential, which facilitate app-to-Azure authentication through the use of secrets, certificates, or assertions. Local development is streamlined through developer tool credentials. These enable developers to use their existing login sessions from tools like the Azure CLI, Azure PowerShell, or Visual Studio Code, represented by classes such as Azure CLI credential and Azure PowerShell credential. In cloud-native environments, Managed Identity provides a highly secure option. The Managed Identity credential is tailored for resources running within the Azure Fabric, allowing them to authenticate to other services without needing to manage explicit credentials. For Kubernetes and federated scenarios, Workload Identity credential has become the modern standard for workload identity management. Finally, composition types like chained token credential and the widely used default Azure credential allow developers to chain multiple credential types in a specific sequence. This ensures that an application can seamlessly transition from a developer's local machine to a production environment by automatically selecting the appropriate authentication method for its current context. As shown here, each credential type maps directly to a specific Go constructor within the AZ identity package. This provides a very intuitive and consistent developer experience. For example, if you are working with an environment credential, you will use the New Environment Credential function. This straightforward naming convention continues through Client Secret Credential, Azure CLI Credential, Managed Identity Credential, and Workload Identity Credential. It is particularly important to note the default Azure credential. While it follows the same naming pattern with its new default Azure credential constructor, it functions differently than the others. Rather than being a single credential type, it is a pre-configured chain of many of the credentials listed above. This design provides maximum portability as it allows your application to automatically select the most appropriate authentication method based on its current execution environment. Moving into Part 2, we address the core decision facing many architects today, the choice between managed identity and workload identity. This selection essentially boils down to choosing between infrastructure-bound and workload-bound authentication models. We will examine how each approach impacts security and management within your environment. The core distinction between managed identity and workload identity is defined by scope. Is your identity bound to the machine or the code? On the left, managed identity, implemented via the Managed Identity credential, ties the identity directly to the Azure infrastructure. This is the optimal approach for resources such as virtual machines, app services, and Azure Functions, where the identity is provided by the underlying host. Conversely, workload identity, using the Workload Identity credential, ties the identity to the software workload itself. This model provides greater flexibility and portability, making it the preferred choice for Kubernetes pods, GitHub Actions, and complex multi-cloud jobs. Determining whether your identity should be rooted in the infrastructure or the software workload is the first step in building a secure authentication strategy. Managed Identity provides a secure, Azure-native way for your applications to authenticate to services without managing credentials manually. This process relies on the Instance Metadata Service, or IMDS, which is a REST API available at a well-known, non-routable IP address. 169.254.169.254. As illustrated in the workflow, your Go application running on an Azure VM initiates an HTTP GET request to the local IMDS endpoint. The IMDS then communicates with Microsoft Entra ID to fetch an OAuth access token. This token is then returned directly to your application. Because this endpoint is only accessible from within the Azure resource itself, it provides a highly secure authentication boundary. Furthermore, Azure handles all aspects of credential rotation automatically, significantly reducing the risk of secret leakage. Implementing this in Go is straightforward using the As Identity package. For a system-assigned managed identity, you can simply call new managed identity credential with a nil parameter. If you are using a user-assigned managed identity, you define a managed identity credential option struct containing your specific client ID and pass that into the same function. This abstraction allows your code to remain clean while Azure handles the complexities of identity management. Workload identity represents a modern, federated approach to authentication using OpenID Connect, or OIDC. This mechanism establishes a direct trust relationship between an external token issuer, such as Azure Kubernetes Service, and Microsoft Entra ID. Unlike traditional managed identities that rely on a hidden metadata server, this process is transparent and built on industry standards. Looking at the flow of how it works, the process begins when the AKS mutating webhook injects a signed JSON web token into the pod. The application, shown here as a Go app, reads that JWT and sends it to Microsoft Entra ID. Entra ID then validates the federation between the cluster and the identity provider. Once the trust is verified, a security token is returned to the application, allowing it to access protected resources. The implementation is designed to be developer-friendly. In the Do code snippet provided, you can see that the new workload identity credential constructor automatically discovers the injected token and relevant environment variables, like the Azure Tenant ID and Client ID. This removes the need for manual configuration and eliminates the risks associated with managing long-lived secrets. This side-by-side architectural comparison highlights the key differences between managed identity and workload identity. Starting with primary scope, managed identity is infrastructure-bound, typically assigned to VMs and POS services. In contrast, workload identity is workload-bound, focused specifically on pods and containers. This leads directly to their level of granularity. Managed identity operates at a coarse node or VM level, while workload identity offers fine-grained control at the individual pod level. When we look at the protocols used, managed identity relies on the instance metadata service via local HTTP. Workload identity utilizes OIDC for a federated exchange. In terms of setup complexity, managed identity is low, whereas workload identity is considered medium. Secret management is highly simplified for both. Managed identity is completely handled by Azure, while workload identity uses injected temporary tokens. Finally, considering use case fit, managed identity is the standard for Azure native POS and VMs. Workload identity is the preferred choice for Azure Kubernetes Service, multi-cloud scenarios, and CI/CD pipelines. The architect's decision framework provides a clear roadmap for selecting the right Azure identity credential based on your application's environment. When you are building on Azure Kubernetes Service, the recommended choice is Workload Identity Credential. This provides granular control at the pod level, serving as the modern replacement for the deprecated pod identity while strictly adhering to the principle of least privilege. If your workload is running on POS services like Azure App Service or Azure Functions, you should use Managed Identity Credential. These services feature a one-to-one relationship between code and compute, making the simplicity and robustness of a system-assigned identity the most effective solution. When designing a library meant to run across various environments, default Azure Credential is the standard recommendation. Its intelligent chain order prioritizes modern patterns, checking first for environment variables, followed by workload identity, managed identity, and finally developer tools. This ensures your code automatically adapts to its surroundings, whether it is running in production or on a developer's local machine. In this third part of our series, titled The Secure Blueprint, we will transition from theoretical concepts to practical application. We will explore a production-ready Terraform implementation specifically designed for Azure Workload Identity. This section focuses on providing a robust, scalable, and highly secure framework that can be immediately integrated into your enterprise infrastructure. The cornerstone of security in a Kubernetes environment is robust namespace isolation. By enforcing a unique namespace for each application, we establish a hard cryptographic lock within the authentication chain. This level of security is achieved because the OIDC subject claim hard-codes the identity to a specific namespace and service account, following the format system/service account, followed by the namespace and then the service account name. On the left, we see a common but risky configuration where multiple applications, such as App A and App B, share the default namespace. This lack of isolation opens the door for potential impersonation, where one application could assume the identity of another. In contrast, the good example on the right demonstrates proper isolation. By placing App A in the App A namespace and App B in the App B namespace, we leverage the Kubernetes namespace boundary. This structural separation ensures that identities are non-transferable and strictly contained, providing a foundation for a secure and trustworthy infrastructure. The subject claim acts as the lock, and the CLI command serves as the key. When you create a federated credential, you are explicitly defining the specific service account that Azure is authorized to trust. Looking at the Azure CLI command provided, we see the process for creating a federated credential named payment-API-federation. The most vital part of this configuration is the -- subject parameter. In this instance, it is set to system-service account-payment API-payment-SA. This specific line represents the critical security boundary of the implementation. It instructs Azure to exclusively trust tokens issued for the payment-SA account located within the payment-API namespace. By being this specific, you ensure that only the intended workload can assume the managed identity, providing a robust and granular layer of security for your cloud resources. This slide outlines the Terraform blueprint for establishing workload identity federation between an Azure Kubernetes service cluster and Azure Active Directory. The process is broken down into 3 essential steps. First, we must enable OIDC and workload identity on the AKS cluster resource. By setting both OIDC issuer enabled and workload identity enabled to true, the cluster will begin exposing its OIDC issuer URL, which is a prerequisite for the federation process. The second step involves creating a standard user-assigned identity. This identity will eventually be the principal that holds the necessary Azure permissions for your application workloads. Finally, we bridge the gap using the Azure RM Federated Identity Credential resource. This is where the actual link is established. The parent ID points to the user-assigned identity we just created, and the issuer attribute links back to the AKS cluster's unique OIDC URL. The subject field is the critical security lock. It must precisely match the Kubernetes namespace and service account name that your application is using. When these 3 components are correctly configured, your Kubernetes pods can securely exchange their tokens for Azure AD access tokens without the need for managing secrets. The Terraform configuration opens the door on the Azure side, but your Kubernetes manifest must present the correct key to pass through it. To establish the secure link, we focus on 2 primary fields within the Terraform resource. First, the issuer must be mapped to your cluster's OIDC issuer URL. This ensures that Azure trusts your specific Kubernetes cluster as a valid identity provider. Second, the subject must follow the precise format of system-service account, followed by your namespace and service account name. This acts as a cryptographic lock, ensuring that access is restricted to requests coming from the correct pod. To finalize this handshake, there is one critical next step. You must annotate your Kubernetes service account with the client ID of the Azure RM user-assigned identity. This annotation informs the AKS webhook which specific Azure identity the pod is authorized to impersonate. Completing these steps establishes a secure, passwordless connection between your cloud infrastructure and your containerized workloads.